Well, I think it's time to talk about Quiz 9, and we're going to walk through the problems and do our best, and well, we'll do more than our best. Let's take a look and see these problems, because they're good problems. All problems are good problems. All right, so number 1. We have the following function, which is continuous and differentiable for all x. So it's x cubed plus 2x squared minus 4x plus 2. That's if we're less than or equal to 1. And 3x minus 2 if we're greater than 1. And for the interval from negative 4 to 2, find all values of c that satisfies the mean value theorem. There's a hint about f of negative 4. Now notice it says all values of c, not just one value of c or two values of c. We want to find all of them. Now we are told that it is continuous and differentiable for all x, which means we can apply the mean value theorem. And in particular, 1 is okay. In other words, there's really no problem for number 1. So it's smooth. All right. So what does the mean value theorem say? Well, it's always good to remind ourselves. It says that the instantaneous rate of change is equal to the average rate of change. So, in other words, we're going to look at how the function changes over the entire interval, and that's the average rate of change, and then we're going to compare it to an instantaneous rate of change. So first off, if you're doing mean value theorem problems, you should compute that value. So here, our a and our b are negative 4 and 2. So we want to look at f of 2, subtract f of negative 4, divide that by 2, subtract negative 4. Now, the top, f of 2. Well, 2 is definitely bigger than 1. So we're going to use this rule. 6 minus 2 is 4. Subtract negative 4, which means we should use that rule. Wait a second, hold on. It gave us a hint. F of negative 4 is negative 14. All right, let's use our hint. Minus 14. And then downstairs, we have, again, 2 minus minus 4. Well, 4 minus minus 14 is 18. And 2 minus minus 4 is 6, which means our average rate of change is 3. So, what are we looking for? Well, we're looking for some place where the derivative is 3. Okay, so the next thing we should do is we should find the derivative. All right, so the nice thing is, if I have a piecewise function, I also have a piecewise derivative. So, if we take our derivative, we would have, sort of the first part, will be 3x squared plus 4x minus 4, and that's it. That's it. And okay, that's if we're below 1. And sort of the second part will be 3, and that's if we're above 1. Okay, so now we have to look at these pieces individually. So, we start with this one. When does 3x squared plus 4x minus 4 equal 3? Well, bring the 3 across. That says 3x squared plus 4x minus 7 has to equal 0. Well, does it factor? Well, I think by now we're pretty convinced almost everything factors, right? So the question is, how? Now, one thing you can do is you can almost guess. You can see the coefficients are really nice, 3, 4, minus 7, which means if you plug in 1, that's a root. So that says x minus 1 is a factor. Once you know x minus 1 is a factor, it forces everything else, because I have 3x squared. So I say, well, x times what gives me 3x squared? It's x times 3x. Here there's a minus 1. You say, okay, minus 1 times what gives minus 7? Well, plus 7. So that tells us x equals 1 and x equals negative 7/3. Now, do we include either one? Well, we have to check. Is it between negative 4 and 2, and is it below 1 or equal to 1? Well, yes, for both cases. For 1, definitely negative thirds is below 1. So negative 7/3 is like negative 2 1/3. So it's in between negative 4 and 2. Okay, so we're definitely going to include these points. Now that's if the first case. How about the second case? Well, the question is, for what values of x does 3 equal 3? Okay, and the answer is, turns out, this is true for all values of x. And you might say, well, wait, where does x show up? Exactly, there is no x. And so regardless of what x you choose, it's always the case that 3 equals 3. So in particular, this works for all values of x, well, in the range, greater than 1. But remember, if we satisfy the mean value theorem, we have to be in x in the interval. And not just in the interval, we also don't want to be at the endpoints. Mean value theorem says strictly on the inside. It's an inside job kind of result. So I need to be above negative 4 and below 2. So it's all values of x greater than 1 and between negative 4 and 2. Well, if you put those together, that gives you values of x between 1 and 2. All right, so this is all of them. So let's put them together. Well, so the answer is there's negative 7/3, which is sort of an oddball. And then notice that this one I can combine, just say, look, include 1. And so 1 up to 2, we put it in the interval notation, it would look like that. Or we could write it as negative 7/3 and 1 less than or equal to x less than 2. Anyways, however you write it, that's it. Now, notice in particular, how many are there? Because it said, find all the values. How many did we find? Can you count? Well, 1, infinity. All right, so there's a lot. There's a lot. Well, that happens. We know it happens because it just happened. All right, good. Well, that's number 1. All right, number 2. Find the unique, that means there's only one, unique value c that satisfies the mean value theorem for the function f of x is arctangent sine of x on the interval 0 less than or equal to x less than or equal to pi over 2. You already know, even before starting this problem, that this is going to be a great problem. You might say, how do you know that? Because we see that. Arctangent. Whenever you see arctangent, you know the problem is going to be good. All right. Well, we're going to do the same process, right? Because it's the same type of problem. It's just a chance for us to practice. In some sense, what's happening with the mean value theorem is a sort of a little bit of practice of saying, let's practice setting the derivative equal to a value and solving. So, as a reminder, what do we have? Well, we're looking for f prime of c equals f of b minus f of a, divide that by b minus a. Now, in our case, b and a, well, b is pi halves and a is 0. So, we're going to take f at pi halves minus f at 0, divide that by pi halves minus 0. Well, pi halves minus 0 is pretty easy. That's pi halves. Now, let's test our ability to do things mentally. So, we plug in pi halves. So, this is an onion type problem. Do it one layer at a time. What is sine of pi halves? Sine of pi halves. What is that? Well, it's 1. All right. Because you can remember, you can think of it in terms of the unit circle. So pi halves would be over here. So that would be your point on the unit circle. And the sine is the y value. So it's that 1. Okay. So now we're arctangent of 1. What angle, when we take the tangent of it, gets us 1? And the answer is pi over 4. All right, 0. Sine of 0, 0. Arctangent of 0, 0. So pi over 4 minus 0, divide that by pi over 2 minus 0. Well, you can simplify that. In fact, it's not so hard. That's the same as pi over 4 times 2 over pi, because you can bring the bottom up, flip it over. The pi's cancel, and 2 over 4 gets us 1/2. All right. So now we say, okay, cool. That says we need to set the derivative equal to 1/2, which means we need to find the derivative. So here's our function. What's the derivative? So, derivative of arctangent. Well, arctangent, the rule is you take 1 over 1 plus the square of the inside. So 1 over 1 plus whatever's on the inside squared. In our case, the inside is sine of x. But remember, chain rule. Then you have to multiply by the derivative of the inside, which is cosine x. Now, what do we want to do? Well, the answer is we want to set this to 1/2. Because we want to know when does the derivative equal to 1/2. So, set it equal to 1/2. Now our goal is solve. Well, that shouldn't be too bad, right? How hard could that be? Well, There's fractions here. Fractions, they're challenging. I've always been challenged by fractions, and so one of my goals is, when I see a fraction, to get rid of it. How can we get rid of it? Well, we can cross multiply. So if you cross multiply, you'll get 2 cosine of x, right? The 2 times the cosine, equals 1 times this denominator, so 1 plus sine squared of x. Well, it's not so clear how to do this. Part of the problem is you have a cosine here and you have a sine. It's like apples and other kinds of apples. They're not quite fully compatible. So what can we do? Well, you always think, is there a trig identity? So, for instance, is there some way I can write this cosine in terms of sine? Or is there some way I could write this sine in terms of cosine? Well, notice that's sine squared. And there's this nice little identity that says if you take cosine squared plus sine squared, you get 1. So what we can do is we can replace the sine squared by 1 minus cosine squared. Now, why are we doing that? Well, we want to get things so that they look more similar to each other. So instead of having cosine and sine, now we have cosine and cosine. So things look more alike. Now, it doesn't mean that it's easier, necessarily. It doesn't mean it's trivial, but at least things are more compatible. Let's put everything on one side. Oftentimes when we're solving an equation, we like to set something equal to 0. And the reason is we're hoping maybe we'll get some nice factoring or something else. So if we pull it across, we get cosine squared of x, which for some mysterious reason, I'll write that as cosine of x squared, plus 2 times cosine of x minus 2 equals 0. Now, what do you see? Do you see it? What's this on the left-hand side? It rhymes with schmoadratic. It's a quadratic, right? You can think of it as something squared plus 2 something minus 2 equals 0, where the something is cosine x. But just for a second, we'll give it a different name. All right, well, that's good. So now we do what we always do, which is we factor, right? So we factor, and life will be good, and I don't think that factors. Uh-oh. It's not factoring. We're in trouble. What do we do? Is it possible? Is it possible to have a quadratic that doesn't factor? Turns out it's very possible. We've been spoiled. Well, okay, so what do you do if it doesn't factor? Well, you look for other methods. Now, it turns out that if you do have a quadratic, there's a formula for that. So, it says that this value for y, well, it's negative b, so minus 2 plus or minus the square root b squared minus 4ac. So 4 times 1 times negative 2. So minus 8. All of that divided by 2a. Now if you clean that up, minus minus of course becomes plus. Square root of 12. Well, 12 is 4 times 3, so you can pull out a 2. So this is really negative 2 plus or minus 2 root 3 over 2. And you can cancel off all the 2's. Doom, doom, doom. So it was important that that 2 was there. We couldn't cancel just that 2 and that 2, because remember that you have to make sure that you get everything. So it looks like we get two possibilities. Negative 1 plus or minus root 3, right? Because I say 2 because there's a plus or minus. So there's negative 1 plus root 3, and there's negative 1 minus root 3. Now wait a second, hold on. Something's weird here. We were told that there's a unique one. Now the word unique means there should only be one. One of these is an imposter. Which one? So which one of these doesn't belong? And why? Well, let's remember something. You see this y? It was representing something. It was cosine of x, right? So the question is, which one of these could cosine of x equal? Is it possible for cosine x to be negative 1 plus root 3? Probably. Is it possible for cosine x to be negative 1 minus root 3? Well, wait. Did you say negative 1 minus something? What? That doesn't feel right. What do you know about cosine? Now, cosine, beautiful function. It goes up and down. But it doesn't go very far up and down. Where does it go up and down between? What's the largest it can be? 1. What's the smallest it can be? Minus 1. So whatever the value is for cosine, it can only be between negative 1 and positive 1. Minus 1 minus root 3, it's too negative. So I can't have that be my cosine. Okay, good. So we're almost there. See, our goal is to solve for this x. That x we find, that's our corresponding c. So we're really close. We've gone it down to the point where that says cosine of x is equal to negative 1 plus the square root of 3. Now, the last thing is, that's cosine of x. We just want x. How do we get rid of the cosine? So right now, x is trapped inside the cosine. How do we free it? How do we release it from its prison? Well, we have to undo cosine. And the way we do it is arc cosine, or inverse cosine. Now I like to use the arc notation because sometimes if you write cosine to the negative 1, it's easy to misinterpret it. And one last thing I'll do is negative 1 plus root 3 is the same as root 3 minus 1. It just looks a little bit better that way, so I'm going to write it that way, root 3 minus 1. Now you might say, wait a second, do we know arc cosine of square root of 3 minus 1? And the answer is, yes, it's called arc cosine of square root of 3 minus 1. It doesn't simplify anymore. So that's it. That's the unique C. That's the one that we're after. That's so amazing. You wouldn't have guessed, at least I wouldn't have guessed, maybe you would, that if that was our original function on the interval 0 to pi halves, that the answer would be so unexpected, but yet somehow, at the same time, so beautiful. Oh man, this math stuff is good. They should make everybody take math classes so that they can see the beauty that is mathematics. All right, let's talk about number 3. Again, similar problem. Find all c satisfying the mean value theorem for the function f of x is log of e to the x cubed plus e to the x between 0 and 1. So hopefully after the first couple of these, by this time we should be pretty quick. So we're like, all right, we'll set f prime of c, that's our f of b minus f of a, divide that by b minus a. So in our case, 0 and 1 is a and b. So we're going to look at f of 1, subtract f of 0, divide that by 1 minus 0, also known as dividing by 1. So let's see. That says, what is f of 1? Well, if you plug in 1, you get log of e to the 1 plus e to the 1, also known as natural log of 2e. If you plug in 0, you get e to the 0 plus e to 0, also known as 1 plus 1, which is 2. Now, that looks like it's not a very pleasant number, but we can clean it up a little bit. Because notice you have logs with a subtraction. When I have log of something minus log of something, what does that become? There's a nice rule. Subtraction becomes division. So 2e over 2. 2's cancel. All right. Now what? Well, natural log of e. What is the natural log of e? The answer may not surprise you. It's 1. So the way to see that is when I'm taking the natural log of e, that's the same thing as asking, if I take e to what power, what gives me e? Well, the answer is e to the power 1. So that's what we get. Okay, so that is what we're going to set our derivative equal to, which means that our next thing we should do is take a derivative. Okay, well, how do we take the derivative of natural log of e to the x cubed plus e to the x? Well, it's actually pretty nice because it's a derivative of a log. Now, when you're taking derivative of log, what you do is you take 1 over the inside. So in our case, the inside is e to the x cubed plus e to the x. And then you multiply it by the derivative of the inside. So the inside, that's this piece right here, derivative of the inside. Well, the derivative of e to the x cubed, that would be e to the x cubed times the derivative of x cubed, which is 3x squared. And then derivative of e to the x, which is e to the x. Okay, so there's our derivative. We're going to set that equal to 1. Equals 1. Well, probably won't surprise you what we're going to do next. Let's get rid of our fraction. So, e to the x cubed times 3x squared plus e to the x is equal to e to the x cubed plus e to the x. Now, what can we do? Well, if we've lived a good life, a good, clean, calculus, algebra life, things should simplify. E to the x is gone. Nice. All right. So that says e to the x cubed times 3x squared has to equal e to the x cubed. They might say, well, let's just keep canceling stuff. Well, what do you want to cancel? Well, both things have an e to the x cubed. Let's cancel those. How would we do it? Well, one thing we could do is we could divide. Divide both sides by e to the x cubed. And that would cancel it. But hold on. Are we allowed? Now you're probably thinking, yeah, of course we're allowed, but are we? Are we? Are we? Why do I hesitate? Well, if you're ever going to divide to cancel, there's something that you have to be careful about. You have to make sure that when you divide, that what you're dividing by is never 0. E to the x cubed, can that possibly be 0? And the answer? No, it can't be 0, because it's e to something, and e to something can never be 0. So we're okay. Good. It's good to always double check, because you never know when they're going to have something subtle. So it's always good to be careful. So 3x squared equals 1. That says x squared equals 1/3, which says, take the square root, you get x equals plus or minus the square root of 1/3. Now the question is, do we keep both? We should have at least one, right? Because this function, it's a nice function. It's continuous, it's differentiable. We know it's differentiable because we took a derivative. Well, remember, we're between 0 and 1. That gives us two values, but are both of them between 0 and 1? Well, not the negative one. So we only keep the positive one, which means that there's only one. So in this case, all c is just 1c, and it's the square root of 1/3. Only keep the positive one. All right, and that's it, right? Good, good. Well, these are fun problems. We should put these on exams. Well, all the problems are fun problems that should go on exams. All right. Oh, a different kind of problem. Number 4. On what intervals is h of x, which equals x squared minus 2, arctangent of x squared, increasing? And on what intervals is it decreasing? Well, again, wow, another arctangent. This is great. A double arctangent quiz. Best quiz ever. Yeah. All right. So, notice it's asking about increasing, decreasing. So, what gives us information about increasing, decreasing? The answer may not surprise you. It's the derivative. So, the derivative, when that's positive, we think of that as being increasing. And where the derivative is negative, we think about that as decreasing. So really, what this problem can be rephrased as is, when is the derivative positive, when is the derivative negative? Now there is some sort of technicality. It's not quite true, this relationship, but it's true enough. It's true enough. We can extend it sometimes, and we'll get into that towards the end of the problem. So let us begin. Well, we need to understand the derivative. I wrote f, but I should have written h. Oh, that's okay, close enough. So let's look at h prime. What is the derivative? Well, the derivative of x squared is 2x. And minus 2. Now we've got to take arctangent. Well, I think by the end of this semester, you'll be really good with arctangent. 1 over 1 plus the inside squared. So in our case, the inside is x squared squared, times the derivative of the inside, which is 2x. So we have 2x minus 2 times 2x is 4x. Divide that by 1 plus x to the 4th. Now our goal here is to try to get a handle on what's the derivative doing. So what we should do is we should simplify it. And in our case, we should try to add these terms together. Well, how do we add? The answer is we get a common denominator, which should be 1 plus x to the 4th, because this 2x is really 2x over 1. So this is 2x times 1 plus x to the 4th divided by 1 plus x to the 4th minus 4x over 1 plus x to the 4th. Okay, good, because, yes, yeah, that's true. So what is that? Well, we get 2x plus 2x to the 5th minus 4x, all divided by 1 plus x to the 4th. And, well, we can do some other stuff here. So that's 2x to the 5th minus 2x. Divide that by 1 plus x to the 4th. Now, let's work on the upstairs. Downstairs, 1 plus x to the 4th, that's always going to be positive. And really, that says the sign is going to be determined by the upstairs part. Both terms have 2x, so let's pull that out. That's 2x times x to the 4th minus 1. Now, what can you do with x to the 4th minus 1? Does that simplify any? And you might say, well, I don't know, that's a 4th power. But secretly, it could also be thought of as x squared squared minus 1. And if you think of it that way, heck, we'll even throw a square on there. It's like, ooh, that's a difference of squares. So that becomes 2x times x squared minus 1 over x squared plus 1. Divide that by 1 plus x to the 4th. And we can go one step further, because now x squared minus 1, that really is a difference of squares. So that's 2x times x minus 1, x plus 1, x squared plus 1. That's divided by 1 plus x to the fourth. Okay, this is, we took the derivative and we simplified it as much as we could. Now you might argue that it seemed a lot simpler when we were up here, but it's simpler in the following sense. It's simpler in the we understand the behavior sense. And that whereas in this original form, it's not quite clear how to recover the behavior, in this form here, it's now not so bad. So how do we proceed? Well, what we look for is you look for critical points. So critical points are where we can switch from increasing to decreasing and vice versa. So looking at this, is there anywhere where it's undefined? No. It's defined for all values. Okay. There's no boundary points because the function is defined for everything, and there's no restriction given in the problem. So the critical points are where we get zeros, and that'll happen upstairs. Now the x squared plus 1, never 0. So we have these three pieces, x, x minus 1, x plus 1. Well, we can read off. That'll be 0 at 0, 1, negative 1. So those are our critical points. So let's draw a number line. So we're going to mark our points, negative 1, 0, positive 1. Now the next thing for us to do is say, all right, we have these pieces. What happens on each piece? So it's like we took our real line and chopped it, boom, 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 boom. And now there's 4 parts. And we're going to do each part individually. So we just go through part by part. So let's start with this part on the far right. Pick a number bigger than 1. You could pick 2, you could pick 200, you could pick 2 million. We don't really care about the value, we care about the sign. We're going to see the sign, and it's going to open up our eyes when we see that sign. Notice a couple things. This is positive, and the 2, just the 2, that's also positive. So the sign is determined by these 3 pieces. So if I pick the number 2, again, just the sign, positive, 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 multiply them all together, that says that h prime is positive. All right, between 0 and 1, pick a half. Positive, negative, because that'll be negative a half, positive. Multiply that together, we get a negative out. How about negative a half? Negative, negative, positive. Multiply those together, we're back to positive. How about negative 2? Negative, negative, negative. So that says our derivative is negative. All right, so now we're almost there. We're ready to write down our answer because we can read off the signs. The signs are right in front of us. So we do the following. We say we are increasing. We're going to look for where it's positive. Well, between negative 1 and 0. And, okay, I've got to pause for a second here and tell you that there's a little bit of controversy, even among the faculty and the instructors. There's not 100% agreement on this. And the question is, all right, should we be increasing negative 1 to 0 but not include the endpoints, or should we be increasing and do include the endpoints? And my personal opinion is you should include the endpoints because increasing is always about comparisons. It's not one individual point, it's about over an interval of points. And other people say, no, you shouldn't include the endpoints because increasing is about the derivative, whether it's positive or negative. And so we've come to the conclusion that we won't care about the endpoints. So whether you include the endpoints or not, you get you get full credit, let's say it that way. So negative 1 to 0. And then where else? Okay, here. From 1 and keep going forever to infinity. Where are we decreasing? Well, now we look for where it's negative. Well, it's negative over here. So negative infinity up to -1, and over here 0 to 1. And that's our answer. Ah, what a fun problem. What a fun problem. All right, good. Okay, let's do our next problem. Number 5. Find the two critical points of y equals x to the 2/3 e to the power -2x over 3, and use the first derivative test for each point to determine if they are local min, local max, or neither. All right, well, let's find the critical points. Now, no boundary. It looks like it's defined everywhere, the function at least. Let's talk about the derivative. So, we're going to look at y prime. Now, here, what rule do we need to take this derivative? Well, we see there's two things, and we're producting them together. Well, we never actually use that phrase, but we're multiplying. So we need the product rule. So I like to think of the product rule as it's everybody gets a chance. So take the derivative of the first one. That would be 2/3 times x to the -1/3. The second one stays alone, e to the -2x over 3. Then we're going to add to that the first one, and now it's the second function's chance. So that'll be e to the -2x over 3. And then we're going to multiply that by the derivative of the inside. So the derivative of -2x over 3, well, that would be -2 over 3. Now we should simplify. Now here, when you have things being added together, well, the way we would simplify is to say, well, let's pull out what's common. So what is common? Well, they both have 2/3. So we can pull that out. What else do they both have? Well, they both have an e to the -2x over 3. Okay, so we'll pull that out. What else do they both have? Well, they both have powers of x. Well, so we should pull out x to some power. Now, which power should we pull out? X to what power? Now, the rule is pull out the smaller power. Which one is smaller? This one. Because it's a -1/3. That's smaller than 2/3. So x to the -1/3. All right, so these are the pieces we're pulling out. Let's see what's left. From the first term, we got the 2/3, we got the x to the -1/3, we got e to the -2x3. Well, that means we got everything. It's all there. Which means that from the first term, we get a contribution of 1. How about from the second term? Well, we got the e to the -2x over 3, we got the 2/3. We didn't get the minus. So there's a minus. What about this? X to the 2/3. We pulled out x to the -1/3. What's left there? The answer is x. Now, why is it x? Well, one thing you can think of it is whatever you pull out, you subtract from the x one. So we're going to take 2/3, subtract -1/3. And if you do that, that'd be 2/3 plus 1/3 or 3/3. Now, another way you can convince yourself that this is correct is imagine if you were to multiply this out. What would you get? Well, it would be x to the 1 minus 1/3, which is x to the 2/3, which is good. Okay, now, where are the critical points? Now, we have a hint. There should be 2 of them. Now, you might say, how do we know there should be 2 of them? Because it says 2. That was sort of our clue. So, well, there's a critical point coming from here. Do you see it? It would be x equals 1. And that would be where the derivative equals 0. How about, is there anything from here? Nope, nothing from there. I know that looks like an x, but that's just sort of like, nope, nothing there. Why? Well, because e to the -2x over 3 is always defined, and e to anything is positive, 2/3 is always positive, so we're never going to get zeros out. How about here? Well, yeah, right, there's a problem. Where is it, though? It's at 0. Now, why? Well, that's the place where derivative is undefined. Okay, So our critical points are at 0 and 1. All right, so we can make a list. Critical points are x equals 0, x equals 1. All right, they might say, why did you leave space? Well, because remember, we have to find the critical points and test to determine if they're a local min, local max, or another. So we're not done yet. So how do we do the test? Well, draw the line. Mark your points. 0, 1. Okay, so there are our 2 points. Now what we do is we pick values. So come over here and pick a value bigger than 1. And again, it can be any number. 2 is fine. So you go through term by term. And this is why it's really nice to have the derivative as a product. Because once you have the derivative as a product, it's really easy to see positive, negative. So the first part here is always positive. 2 to negative 1/3, positive. 1 minus 2, negative. That tells us the derivative is negative. Okay, between 0 and 1, we can pick something like a half. Positive from the first part. A half to a negative 1/3 is still positive. 1 minus a half is also positive, which means that we are going to be positive. Right? Positive, positive, positive. Everything's looking good. It's a very optimistic interval. How about something below 0? Say negative 1. First part's always positive. Let me skip to the end. 1 minus minus 1 is positive. Okay, got to think a little bit. If I take the cubed root, because that's really what's happening here, that 1/3 means a cubed root. A cubed root of a negative number. Is it positive, negative, or undefined? Well, the cubed root of negative 1 is negative 1. It's a negative value. So what that means is that we're going to have this will be negative. So we're positive, negative, positive, and therefore we're back to being negative for the derivative. Now in terms of what's happening, that says below 0 we're going down, after 0 we go up, and then after 1 we go down. So our function is doing something vaguely like that. Now of course it's much more interesting than that. For instance, if you were to plot this x to 2/3, it really looks like this. It's like a cusp. And so, but it doesn't really matter. We don't need to know the form of it. We just need to know the general behavior. And we can see if we come down and then go up, that says 0. What kind of point do we have? Well, it is a local min. Now, at 1, before it, we're going positive, which means we're going up. After, we're going negative. So it means we're doing something like this. We're going up. So what kind of point is it? It's a local max. Go up and go down. That's a local max. And that's our answer. And there we go. That's number 5. All right. Good. Wow, halfway through. And it feels like we barely just began. All right, well, let's go on to the next one. Number 6. Find the 2 inflection points for y equals theta squared plus sine of 2 theta, where theta goes between 0 and pi. Also identify where the function is concave up and where the function is concave down. Now this tells us that there's going to be 2. So, well, we've got to be on the lookout for 2 of them. Now, where do inflection points happen? Well, inflection points are where we change a particular type of behavior known as concavity. See how the problem is asking us about concave up and concave down? So it's where we change from either going concave up to concave down or concave down to concave up. And those have to do with the second derivative. So where the second derivative is positive, we call that concave up. If it were a bowl, that would be a bowl that holds water. So in other words, it looks something like that. Where the second derivative is negative, that's concave down. And if that were a bowl, it would be a bowl where the water would fall out. So it looks something like that. So we're trying to understand the basic shape of the curve. But in both cases, really, it's all about the second derivative. So it's all about the second derivative. Oh, yeah. It's all about the second derivative. It's second derivative. Oh, yeah. Okay, second derivative, right? Well, we better do the first derivative. Okay. Derivative of theta squared, 2 theta. Derivative of sine of 2 theta. Well, derivative of sine is cosine. And then you leave the inside alone, pristine. But then you multiply by the derivative of the inside, which will be 2. Y double prime. Well, the derivative of 2 theta is 2. Then derivative of cosine is negative sine. But again, we've got to compensate for the 2, so we'll multiply by the 2 again. There was already 2 there, which gets us up to a 4. So 2 minus 4 sine of 2 theta. Well, all right. So where can we change concavity? Concavity can change. It's kind of similar to what we were doing where we talk about critical points, but the analog for the second derivative. So we're looking for where is the second derivative 0 or our second derivative is undefined. Well, it's never undefined. This is a relatively good function, which means that we're really after where does the second derivative equal 0. So let's set the second derivative equal to 0. We can move this across, divide by 4, and that gets us to sine of 2 theta equals 2/4, also known as a half. So now we need to remember our trick. All right, so we have our circle, unit circle. Now, what does the sine correspond to in the unit circle? This is a really useful thing to remember. And the sine corresponds to the y values. So that is to say, if I were to pick a point here, then I would have the x would be the cosine of your angle, y would be the sine of your angle. So when I'm saying I want sine to be a half, I'm saying, okay, I set my y value equal to a half, so I'm looking for these angles here. That's when I get sine is a half. Now, don't worry about the 2 theta. Just ask the question, for what angles does sine equal a half? Well, it should be a really familiar angle, right? And we say, okay, well, what does that angle look like there? And, well, it's pi 6. Okay, that's the first time. When's the next time? Well, that would be like if I went pi, but then it went back pi 6. So that would be 5 pi 6. When would be the next time after that? Well, the next time after that, I'd have to go all the way around, then go a little bit more. So it would be 13 pi 6. But that one's going to be too big. Why? Because remember, this is what's being put into our sine. So that's our 2 theta. So if theta went between 0 and pi, then 2 theta should go between 0 and 2 pi. So what we're really looking for is, for what angles between 0 and 2 pi do I get sine of that angle equal to a half? And the answers are pi 6 and 5 pi 6. So what's our choice for theta? Well, pi over 12 and 5 pi over 12. All right. Now, these could be inflection points. Technically, we don't know yet, but they could be. How do we know? What breaks our sort of like doubts? Well, we draw a number line. Now notice this is one where there is a boundary. So we have 0. We don't go very far. There's pi over 12. 5 pi over 12 is over somewhere near here. And then pi way back over there. All right. So now we have to figure out the signs for the second derivative. And the nice thing is, we didn't mention this before, but it's good to mention it now, right? We still have time. There's lots of problems left to do. Is if we're trying to understand the sign of something, and here I'm not talking about the sign function, I'm talking about positive, negative, you just have to look for any arbitrary point in the interval. So pick nice points. When you have a choice available, or when you're asked to make a choice, always pick the one that's easy to work with. So let's think about what's below pi over 12. Is there a convenient number below pi over 12? Anything coming to mind? Any number below pi over 12 that looks like it would be very easy to work with? Do you see something that could do it? Oh yeah, 0. 0 is below pi over 12. Okay, let's plug in 0. What do we get? We get 2 minus 4 times 0, which means it's positive. So, second derivative is positive below pi over 12. How about this other end? From 5 pi over 12 to pi. Well, again, let's pick pi. Sine of 2 pi is still 0. So we still get 2 minus 0. So that says our second derivative is positive. All right, between pi over 12 and 5 pi over 12. Well, let's split the difference, right? What's halfway between? It would be 3 pi over 4. Sorry, 3 pi over 12, which is pi over 4. How do I get halfway in between? Well, just add and divide by 2. See, if I add these, I'd get 6 pi over 12, which is pi over 2. Divide by 2 says that halfway in between would be pi over 4. Now, 2 times pi over 4 would give us pi over 2. Sine of pi over 2 is 1. So it becomes 2 minus 4, which is negative. So our second derivative is negative here, which means that pi over 12 and 5 pi over 12, these are indeed inflection points because we flip the sign. Concavity changes. So our answer, the inflection points are at pi over 12 and 5 pi over 12, and we're concave up from 0 up to pi over 12 and 5 pi over 12 up to pi. So these are concave up, and we're concave down from pi over 12 to 5 pi over 12. And, oh my gosh, this is a case where writing down the answer takes a non-trivial amount of space, but that's the answer. All right, there we go. That's that one. All right, good. All right, what's next? Well, I suspect that after number 6, we should talk about number 7. Find and classify the critical points of h of x, which is e to the x, divide that by 4x squared plus 3. Now notice, it's not saying first derivative or second derivative. It's kind of like dealer's choice. Now, which one should we pick? Well, let's take the first derivative and see how we're feeling. But generally my philosophy is, if the derivative is non-trivial to take, stick to just the first derivative. If the derivative is super easy to take, go ahead and do the second derivative. So, what rule do we need to use to take that derivative? We have a function divided by a function. So our rule will be the quotient rule. Quotient rule says you take the bottom and you multiply that by the derivative of the top, which is e to the x, subtract the top, e to the x, divide that by the derivative of the bottom. Well, derivative of 4x squared plus 3 is 8x. And all of that is going to be divided by the bottom term squared. Well, we can clean that up. We don't need to worry about the denominator. It's always going to be positive because it's 4x squared is always greater than or equal to 0. 3 is definitely greater than 0. It's 3. So add them together, it's positive. If I square it, it's still positive. So the denominator is never a problem. Upstairs, well, let's factor out the e to the x. You get 4x squared minus 8x plus 3. Downstairs, 4x squared plus 3 quantity squared. And I would say, looking at this, let's pause and just say, I don't want to take another derivative. So yeah, we're going to stick with the first derivative test. Now, we're not done because we still have to find the critical points. What's left? Well, probably this 4x squared minus 8x plus 3. We'd like to clean that up a little bit. And the question is, can we do it? Well, what would be nice? it would be really nice. In fact, really, really nice if it factored. Now, I know that after our problem earlier, you're probably like, I don't know. I don't know if anything's going to factor anymore. But, please try factoring. You'll discover a surprisingly large number of problems do factor. It's just, we get that one problem that doesn't factor every semester. So that was the one for today. All right, so let's just assume we're going to factor. And if we think it's going to factor, can you see what it might factor as? Well, 3, not a lot of ways to break the 3 up, so that's 3 and 1. The fact that we see a plus means they have to be the same sign. This minus says that sign better be subtracted. Now the 4, well, that could break up as 4 and 1 or as 2 and 2. And, it looks like I think 2 and 2 might work. Let's try and see if that works. 2x, we check. 4x squared, that's good. Minus 2x minus 6x. Ooh, that is minus 8x plus, okay, good. It works. Good. Okay, so where are our critical points? Well, we don't have to worry about dividing by 0 because it's never 0. E to the x, can that be 0? No, it can't. Okay, how about 2x minus 3? Yeah, that can be 0 at 3/2. Okay, how about 2x minus 1? Well, yeah, that could be 0 at 1/2. So we have 2 critical points, 3/2 and 1/2. All right, well, that says we got to classify those 2 points. Well, let's draw our 9. We mark our points, and 1/2, 3/2. And now we got to figure out what's happening with the sign. Now let's just make a couple notes. This part down here is always positive. E to the x, that's always positive. So the sign will be determined by these 2 pieces. Okay, let's pick something bigger than 3/2, which by the way is also known as 1.5. So we could pick 2. Positive. So that tells us our derivative is positive. All right, how about something between 1/2, also known as 0.5, and 1.5, 1.5? Well, I think 1's pretty good. That's halfway in between. Negative, positive, right? Because it's going to be minus 1. This will be plus 1. Well, that says, since they're different signs, it's going to be negative. Okay, how about below 1/2? Well, 0. 0 is your, 0 and 1. Those are always your go-to options if you can. Negative. 2 wrongs, make a right. Well, no, not quite. But at least 2 negatives when they multiply do make a positive. So we can now see the behavior. It says we're coming up, we're going down, we're going up again. And so we see that the answer is that our 3/2 is a local min, right? Because we're going down and up. And 1/2 is a local max, because we're going up and then down. And that is, we found them and we classified them. And that's the answer. All right. Number 8. Whoops. Find and classify the critical points of f of x equals 2x to the 5th minus 5x to the 4th minus 10x cubed plus 13. So it's again a similar problem. It's find and classify. So let's start with defined. Okay, so here we go. F prime of x. Derivative of 2x to the 5th is 10x to the 4th, and then derivative of negative 5x to the 4th minus 20x cubed. Okay, that really is a 3. I know that's a terrible looking 3, but that is a 3. Derivative of negative 10x cubed is minus 30x squared. Okay, so now let's look for, okay, it's a polynomial. never undefined. There's no boundary. So we're looking for the zeros. Well, one thing we can do to clean this up is we can factor stuff out. So we can say, okay, pull out 10x squared. And then what's left? Well, it would be x squared from the first term, minus 2x from the last term, and minus 2x from the middle term, minus 3 from the last term. Well, we go by our everything factors belief. So 10x squared, and then what do we have? Well, x. So, well, not really a lot of things to think about, right? We need two things that multiply together to give us -3, but add to give us -2. So, -3 plus 1. That'll do it, right? Because we get minus 3x plus x. So, where are the critical points? Well, we get 3 of them, right? Because we have here the x, that's 0. The x minus 3 would be 3. And the x plus 1 would be -1. So there are our critical points. So, let's draw our line. And we can say, where are our points? We've got -1, 0, and a big gap. Oh, didn't leave myself enough space, but we'll pretend like that's 3 times as big. Okay. Wow. So let's pick some values. So if I pick something, say above 3, like 4. Okay. Well, let's actually make a couple of quick notes. What's true about 10x squared? It's always greater than or equal to 0, right? So really, the thing that determines the sign is the x minus 3 and the x plus 1. So if I pick 4, positive. So that says f prime is positive. Between 0 and 3, I could pick 1, negative, positive. So I'm negative. Between -1 and 0, I could pick a half. And what would that give me? Well, that would be a negative and a positive. So I'm still, f prime is still negative. And something below -1, like -100, well, negative and negative, making that positive. So what does that say? It says I'm coming up, below -1, going down, and then going down again. So this is sort of like, and then I'm going up. Okay, so what are our critical points? So there's 3 critical points. We have -1 and -1, because we go up and down, this is a local max. 0 is neither max or min, right? Because what happens is it goes down, which means it's not the smallest in points nearby, and it's not the largest of points nearby. And then 3, because we're down up, that's a local min. Now, that's our answer. Now you might say, could we have used the second derivative? Let's pause for a second and talk about that. We've got plenty of time. We don't have anywhere to go. So if I had tried to use the second derivative to classify, well, I would have been okay for a lot of it. 40x cubed minus 60x squared minus 60x. Then what you would do is you'd plug in points like -1. You'd get minus 40 minus 60 plus 60, which is a -40. And if your second derivative is negative, well, that means your curve looks like that, your local min. If you plug in 3, you get big number minus a big number minus a big number. And if you were really patient, you would get that it would be a positive value. And if your second derivative is positive, your curve looks something like that, and you're at a local min. Now the problem is if you plug in 0, you get 0, 0, 0. And you might say, well, good. What happens when you have 0, though, is you don't know. your second derivative test is inconclusive, so it's not able to classify it when the second derivative is 0. So even if we had tried the second derivative, the conclusion was we'd have to go whoop and jump back to the first derivative. So the first derivative is a more powerful tool. But that being said, know both rules. Because there are times when the first derivative test doesn't work as well as the second derivative test. And when you go and do multivariable calculus in a year, you want to make sure you know the second derivative test, because that's going to be the one that actually works in multivariables. Number 9. All right. Find all inflection points for y equals 9x e to the minus x squared over 6, and determine the intervals where the function is concave up and where the function is concave down. This is similar to a problem we did a little bit ago, right? And so we know when we're talking about concave up, that's secret code for saying second derivative is positive, and concave down is code for saying second derivative is negative. So it's about the second derivative. So, well, we're just going to be patient and work through this. So, first derivative, what rule do we need? And the rule is we need a product rule. What else do we need? And a chain rule. So, derivative of the first be derivative of 9x, which is 9, e to the minus x squared over 6, and then plus 9x times it by the derivative of e to the negative x squared over 6, which would be e to negative x squared over 6, times the derivative of the upstairs, which would be minus 2x over 6. Let's clean this up. Now, the reason I say we should clean it up is whenever you have to do something with the derivative, you should clean it up. If you have to evaluate it, don't bother cleaning it up, just evaluate it. But if you have to do something, and an example of something is finding where it equals 0, or maybe taking a second derivative. So, since we do have to take a second derivative, let's see, we get 9 e to the minus x squared over 6 is the first term. Plus and a minus means this is a minus. Now notice the 2 over 6 becomes a third. And there's a 9, so that leaves us with the 3. And there's an x and an x, so that's an x squared e to the minus x squared over 6. Okay, that's going to be a little bit more simple to work with. Now the second derivative. Well, for the first piece, that's chain rule. So no real big surprises. So 9 e to the minus x squared over 6. The derivative of that is minus 2x over 6. Right, rid of the inside. Product rule here. So minus derivative of 3x squared is 6x. E to the minus x squared over 6. And minus 3x squared times the derivative of the inside, which is minus 2x over 6. So, let's clean this up. We have a 9. This will be 2 over 6, again is a 3. Well, that goes into 9. Then there's a minus. So let's see this. That's minus here. I want to make sure we get all this. So equals minus 3x e to the minus x squared over 6. Ah, wait a second. Oh, we forgot a term. Can you see it? We said we took the derivative, we kept this function, but we forgot to write down that there's a minus e to the minus x squared over 6. Ah! That's why you double check your work. Okay. All right. Good. Good. Ah, that could have been disaster. It could have been. But it wasn't, right? Because we were careful. And it pays to be careful. Okay, so wait. Back to our regularly scheduled derivative. All right. So we have a minus 6x e to the minus x squared over 6. And then here, minus minus makes a plus. The 3 and the third cancel. So that's plus x cubed e to the minus x squared over 6. Okay. All right. Good. Did we get it all? I think we did. So keep simplifying, right? So we can pull out the e to the minus x squared over 6. And then what do we have? Well, we have the highest power is x cubed minus 3x minus 6x. Makes that minus 9x. Well, I don't think that's too hard to factor, right? Because one thing you can do is you can pull out an x. So that's x times x squared minus 9. And then you're like, wait a second, x squared minus 9, something squared minus 9, which is 3 squared. That's a difference of squares. So x squared over 6, x minus 3, x plus 3. Good. Well, now we can read off where is the second derivative equal to 0. Well, first off, this part will always be positive because it's e to something. So we have our three pieces. We get 0, 3, and negative 3. Now, we haven't yet determined if these are the inflection points. All we've determined is that there are possible inflection points. What we really need to do now is understand what's happening to our second derivative. So we draw our line, and now we test. So we pick values, something bigger than 3. Well, let's say 4. Again, the first term is always positive, so we just go through. Plug in x equals 4. Positive, positive, positive. Okay, that's feeling very positive to me. Second derivative is positive. Now, between 0 and 3, 1, right? 1. Always 1 is a good choice. Positive, negative, positive. So, second derivative, negative. Okay, between 0 and negative 3, how about negative 1? Negative, negative, positive. So that makes the second derivative positive. Okay, negative 4, negative, negative, negative. Very negative. Second derivative, negative. Now this doesn't mean it's going down and up, right? Because this is the second derivative. What this says is we're concave down, the second derivative is negative, concave up, concave down, concave up. Now notice that at these three places, negative 3, 0, 3, we flip behavior down to up or up to down. And therefore, truly at this point, now we can say that they are inflection points. So, the inflection points are at x equals negative 3, 0, and positive 3. We're concave up. Where? Well, from negative 3 to 0, and from positive 3 towards infinity. And we're concave down. And where does that happen? Well, from minus infinity up to negative 3, and from 0 to 3. And that is our answer. There we go. Okay, that's number 9, which must mean the next one is number 10, our final problem. It's kind of sad. We were just warming up, but we're getting pretty good at these, right? Okay, so let's see. What do we have? We have our function is 4 arctangent t. Another arctangent problem? A triple arctangent quiz? Best quiz ever. Cool. All right, anyways, let's not get distracted. All right, there's also a log of t squared plus 1, and there's minus t for some reason. All right. Find the absolute maximum value for the function. Justify your answer. Now, we talked about absolute maxes and absolute mins before, but there's a little bit different twist here, because here, notice our interval is not a bounded interval. See, t greater than or equal to 0, t can be arbitrarily large, which means it's unbounded. So there's no guarantee that this function should have an absolute max. Now, it can, and the claim is that it does, but it means that it isn't just sort of an arbitrarily like a freebie. So that means we got to work for it. Okay, So let's figure this out. Well, as always, if we do have an absolute max, where can it be? It has to be at a critical point, because the critical points are the interesting point. If there's something interesting, it's almost always going to be happening at a critical point. So we start by taking our derivative. Well, the derivative of arctangent, 1 over 1 plus t squared. Derivative of log of t squared plus 1. Well, whenever you're taking the derivative of a log, it's a very straightforward thing to take a derivative. You put the function downstairs, and then upstairs you put the derivative of the function. So that would be 2t. And then the derivative of minus t is minus 1. Now, these are the same, even though they're written backwards, right? 1 plus t squared is the same as t squared plus 1. We want to add this into the mix as well, so we'll make it a 1 plus t squared over 1 plus t squared. Now they all have the same denominator, so that would give us a 4 plus 2t minus 1 plus t squared, all of that divided by 1 plus t squared. And we could clean that up, so that would be minus t squared plus 2t plus 3. Now, of course, we suspect this will factor. I don't like having a minus in front of the t squared. It just makes it harder for me to keep track of things, so I'm going to go ahead and pull a negative out. If I pull a negative out, I'm going to pull a negative out of each term, so be careful. You're not just pulling a negative out of the first term, you're pulling out of each term. And now we ask, okay, does t squared minus 2t minus 3 factor? Well, excuse me, it did just a few problems ago, so I think it probably still will factor. So that will be factored as t minus 3 and t plus 1. Now, look at our function. It says this is our function for t greater than or equal to 0. Where are our critical points at? Well, this one is at -1. We don't care about that one. It's outside of our range. How about this one? Well, it says it's 3. Okay, so really our critical points, as far as we're concerned, are at t equals 3. You see there's one more? Do you see which one it is? It's our boundary, 0. Okay, so those are our critical points. Now, let's think about what happens to our function. So, here's 0, and we start at 0, so we don't have anything below 0. And then we go up to 3, and then we go past 3. So, let's pick a number between 0 and 3. Oh, 1, right? Okay. Minus, that'll be minus, that'll be plus, and that'll be plus. If we put it all together, we see that f prime is positive. Pick something bigger than 3. 4. Minus 4 minus 3 is positive. 4 plus 1 is positive. And downstairs is positive. So, minus positive, positive, positive. The result is it's negative. So we see that before 3, the function goes up. After 3, the function goes down. In fact, you see how it says justify? We can justify. So before t equals 3, the function is increasing. And after, the function is decreasing. And so what does that tell us? Well, it tells us that if we're going up before t equals 3 and we're going down after t equals 3, the conclusion is that t equals 3 must be where the max occurs. So now we say, okay, great. So we now know where it occurs. We can never be bigger than t equals 3, because I can't be bigger than t equals 3 to the left because I'm only going up. I can't be bigger from the right because I'm only going down. So t equals 3 is where the absolute max occurs. Now, but we're after the max value. So the final thing we need to do is we need to plug 3 into our function. So we get 4 arctangent of 3, and arctangent of 3 is arctangent of 3. Yeah, it's just one of those strange things we don't know. 3 squared plus 1. Well, that's 10. Minus 3 is minus 3. And that is our max value. And here's our justification. And we're done with this problem, with the quiz. Ah, what a good quiz. This is actually a really important kind of quiz, to be honest with you, because it's really telling us we can start understanding the behavior of functions by looking at the derivatives, first derivative, second derivative. It's telling us how the function behaves. And once we understand how the function behaves, we can start seeing, okay, when is a point of max or min? And that means that we can start talking about max and mins, which means optimization is just around the corner. And that's a good topic. But we'll have to wait for the next quiz. And that's it for this one. See you later. Bye.